Okay, welcome everybody. Today I have to say that it's a pleasure to introduce you to Adam Burgasser, that is a very well recognized expert on brown dwarf field. Well, he did his PhD in Caltech, and then after full postdoc in the University of California in Los Angeles, and also in the American Museum of Natural History. He got a permanent position in the MIT, like assistant professor, and now he's currently in the University of California in San Diego. Well, I have to say that I know Adam Burgasser since the beginning of my career, when he started to do his PhD with the Thomas team. In fact, he was participating in the discovery of the first L dwarfs, and also he was leading also the discoveries of the first T dwarfs. But not only that, but he was also with Tom G. Ball, one of the responsibles of the classification, of the spectral type classification that we have now for the T dwarfs. He's also very interesting in the studies of binaries, and brown dwarf binaries in particular, and also in the LT transition. And in particular, Marley and he proposed one of the models to explain this transition, this LT transition, through the cloud disruption in this object. And well, he's also now involved in the searches for white dwarfs, which are the coolest ultra-cool dwarfs currently known. And also, he's also very interested in the study of metal-poor brown dwarfs. Well, today he's going to review all these very interesting discoveries and about all the things he had developed during his work. So, Adam, when you want, thank you.
Muchas gracias. Can everyone hear me okay? Okay. Thank you very much for that very wonderful introduction. It's a pleasure to be here and share both a summary of what we've learned about brown dwarfs over the last 20 years, kind of where we are right now with the outstanding questions that need to be addressed by them. And then I'm going to dive a little bit into stuff that I really care about, since it's my talk and I can do that. And that's on spectral binaries. So here's a brief overview of what I'll be talking about today. As I mentioned, an overview. I'll mention some of these outstanding questions. And I'm going to spend a little time talking about a project that I've been running for the last 8 years or so to compile a large sample of low-resolution near-infrared spectra. This is the SpeX Prism library. And I'll touch very briefly on the breadth of science that's coming out of that project. And I'll focus a little bit on this particular class of objects that we call spectral binaries, and how they're also giving us very incredible detail on the physical properties and the evolution of brown dwarfs as we look at the new binary systems. And then I'll close with some sort of overall thoughts about where I think much of this research is going. So to motivate this, I want to, here we go, play this little presentation, this movie that one of my former postdocs, John Verchansky, made using SDSS data. So this is a 1 square degree of sky, and as you're watching it, you'll see these purple triangles come out. These are all the M dwarfs in this image, and every couple seconds or so, it goes down 1 magnitude deeper. And so you can see the field is starting to get more and more crowded as we go to fainter and fainter magnitudes. And it keeps going, and it keeps going. Okay, so hopefully the point being made here is that we are literally surrounded by these little tiny stars, these M dwarfs, the coolest stars that were known up until about, say, 10, 15 years ago. We are literally surrounded by these things in the galaxy. And this was actually known, has been known for quite some time. This is an early plot from Edwin Salpeter back in 1955, making the first mass function measurements of the local solar neighborhood. This is now showing the mass of stars and sort of the units he had went sort of backwards. So you have low mass stars here on the right, high mass stars here on the left, and then logarithmic density of stars in the galaxy. And this line is a line. We love to see lines in astronomical trends. But it indicates that there are a lot more of these very little stars in our galaxy than there are more massive stars. And of course, a question that naturally arises when you see this beautiful trend out to the lowest masses that you measure is how far do these masses actually go? What's the smallest star are there, and how many of these really small dark stars can there be in our galaxy? Now, this is not a purely academic question. For scientists, this could mean gold. Okay, so here's the Nobel count for our sort of different forms of matter energy in the universe. As many of you know, most of the universe is not made out of the stuff that we're familiar with, the baryons and the electrons and leptons. It's only 4%, but it gets a lot of Nobel Prizes for that 4% of mass. Recently, there was a Nobel Prize given to a trio of scientists, and were any of these at Cosmos? I think it was just WMAP was represented. Okay, so Kobe, so these guys weren't here. They'll be here next year for the Cosmos. But they were Nobel Prize for discovering, at least finding evidence for this significant fraction of the mass energy of the universe, dark energy. And of course, we have a lot of people looking for this other component, the dark matter, which actually has a gravitational attractive force throughout our universe. That Nobel Prize is up for grabs. So there's a lot of people looking for striking gold in this particular field. And if you believe that you can have these very low mass stars continue to arbitrarily small masses, then it's actually pretty easy to make up the missing matter in our galaxy with lots and lots of little tiny stars that you can't see because they're so faint. And so it begs the question of how small can a star actually be? Is there a limit to how small these little masses, little fusing objects can be? Now, these objects start off as large balls of gas, and they achieve the potential of fusing by just collapsing down till their core temperatures are hot enough to start fusion. All right, so if you have something like the mass of the sun, you shrink it down to something like the size of the sun, or maybe a little bit bigger, and you extract enough gravitational potential energy to start fusion reactions in the core. And now you've got something that acts like a star. Now, how low can we make this go? If I took this little clicker here, which is maybe something like 100 grams, and I crushed it to the point where I extracted enough self-gravitational potential energy in my clicker to start fusion reactions, you could very easily calculate, just by scaling laws, that I would have to crush this to something like 1/1,000,000th the size of a proton. So clearly, I'm not going to extract any fusion energy from my clicker anytime soon. So there must be a limit. And this limit is actually quite a bit higher than the mass of this clicker. It's actually only about 7% of the mass of the sun. And this is something that was deduced back in the 1960s by Shiv Kumar and independently by Hayashi Nakano, looking at the evolution of different models of stars. So this is now a function, the x-axis here is the core density of these collapsing objects and the core temperature. The magic line here, about 3 million degrees Kelvin, is the temperature you need to achieve sustainable hydrogen fusion. And you can see that most of these lines, in the direction of evolution for all these, is going to higher densities and higher temperatures. They can cross that threshold and begin hydrogen fusion. That's a normal low-mass star. But very low-mass stars have to achieve much higher densities, because there's less mass total, in order to get hot enough in the core. And at some point, you run into a fundamental limit of electron degeneracy. The electrons themselves start to provide the pressure support to prevent any further collapse of these objects. And so if you hit that limit, which is indicated here on this plot, if you hit that limit before you achieve hydrogen fusion, you can no longer collapse this star enough to get hot enough to start fusion reactions. In fact, you will never get this star collapsed enough to start fusion reactions. And so we have here a fundamentally different type of object. It's a star, but it's not doing the things that stars are supposed to do. If stars' jobs are to take protons and make helium and other heavy elements out of them, these are not living up to their job expectations. All right? These are fundamentally different objects. And this translates into the evolution of these objects with time. This is a plot I made from models from Adam Burrows et al. 2001. This is now showing time along the x-axis and the effective temperature, or at least the surface temperature of the stars that we're looking at. At a normal star, which lies up here at the top of this chart, so this starts at about 0.2 solar masses and runs way down into about 2 Jupiter masses. Up here at 0.2 solar masses, a star collapses to the point where it starts fusing hydrogen, and that energy source is enough to compensate for the energy loss at the surface. And so you have something that is in a sustained position. Right? It's producing as much energy as it's losing from radiation. So it stays at a nice, comfortable, effective temperature for an extremely long time. For these 0.2 solar mass stars, this is much longer lifetimes than the age of the universe. But here, these objects, which were not massive enough to reach that core critical temperature, they just continually cool off over time. Like Adam Burrows likes to say that these objects are like charcoals plucked out of the fire. They're glowing red hot when you first pull them, but eventually over time they'll cool off and become darker and darker and blacker, at least to visible wavelengths. All right. And then you can go even lower mass. So that limit is, again, about 7% the mass of the sun. You can go to even lower masses, about 1% the mass of the sun. And those objects don't fuse anything at all. They don't fuse the easiest element to fuse, which is deuterium. And so the IAU and many other people have started to call these things maybe planetary mass objects or planemos. There's all sorts of interesting names to call these objects, and I'll get to that again in a little bit. But the point is that these objects, again, are fundamentally different. They evolve with time. And they evolve to such low temperatures that, in principle, we shouldn't be able to see them. So again, if that mass function from salpeter continues on to, say, a Jupiter mass, then we would have plenty of cool, dark things in our galaxy to make up for all the dark matter. Now, there's one problem with this. They don't exist. Now, I see Nicholas is now shuffling in his feet very uncertainly because this is his field of research. Now, if I did this talk in 1994, I could say this quite confidently. They don't exist. Brown dwarfs don't exist. 20 years ago, we had seen none of these objects. For about 30 years of searching, nothing. Nothing in the sky looked like a brown dwarf, something that was cooling over time, didn't sustain hydrogen fusion. Not a great field to be in at that point. But 1 year later, everything changed, and it changed right here at the IAC. And so this classic paper from Rafael Robolo to Nature reported the result of the first real brown dwarf, the first detection of an object that was not sustaining hydrogen in its core. And the major test for that was the fact that this object, which is a member of the Pleiades cluster, so about 125 million years old, still had lithium in its atmosphere. Now, lithium is an element that fuses at a lower temperature than hydrogen, right, something like 1,000,000 degrees Kelvin. And these objects, these cool stars, because they are so dense, the opacities, internal opacities are so high, they're fully convective. And so any lithium in the star, if the core is hotter than 1,000,000 Kelvin, all of that lithium will eventually be destroyed, usually over the course of about 10 or 100 million years. This object, which is over 100 million years old, clearly had a detection of lithium in its atmosphere. And so this is the first time that we could see chemical evidence that the core temperature of this particular star was not hot enough to fuse hydrogen because it was not hot enough to fuse lithium. Now, about the same time, this object was also found. This is Gliese 229b. This, by the way, this picture, if you go to the American Museum of Natural History in New York City, is hanging up on at sort of super grand scale. Of course, not 2 scale because that would be much bigger, but a very large picture up in the museum. This is probably the only piece of art of brown dwarf science I've ever seen displayed. But there you go. This is actually a Hubble Space Telescope image. Gliese 229a is this really bright star over here, which is actually one of these cool M dwarfs, and so it is itself a faint star. And this little faint object was found originally with the 60-inch at Palomar, but now confirmed with several other telescopes. The fascinating thing about this object was not that we could see that there was lithium in the atmosphere, but that when we looked at its atmosphere, it didn't look like a stellar atmosphere at all. In fact, it looked like a planetary atmosphere. This is H-band spectrums for about 1.5 to 1.7 microns, and it's hard to distinguish these lines, but this line right here is the spectrum obtained for this object, Gliese 229b, and this line right here is the spectrum obtained for a moon of Saturn, Titan. All right. This is not what you would expect when you're looking around in the sky for stars, are moons of Saturn. Now, of course, the reason it looks so similar is because the very strong strength of one particular molecule, which is methane, which takes out most of the absorption, most of the continuum flux, longward of 1.6 microns. But the fact that we could see an object, take a spectrum of an object that looked like a planet, was again a big major leap in our understanding of that this population of brown dwarfs could be potentially very interesting beyond just the discovery of them themselves. Now, a lot of these discoveries and the subsequent discoveries, we now have about 1,000 of these brown dwarfs known in all sorts of environments in the vicinity of the sun and young star-forming clusters as companions to other stars. We're even starting to find them as halo objects with very high motions through our galaxy. This has all been stimulated by advances in near-infrared technology. If you think about it, near-infrared technology is not a particularly old region of the electromagnetic spectrum to human science. The first evidence of it comes from William Herschel's experiments with thermometers and looking at the invisible rays that were coming from the sun. You jump up to about the 1920s when we had the first real detectors that you can put behind telescopes to detect near-infrared light. These are thermocouple detectors. And these were the first observations of things like the moon in the near-infrared. Of course, today we have these things that more look like CCDs. They aren't CCDs. They're not silicon detectors. They're other, depends on the material, but they have other different properties for detecting near-infrared light. I should say that this object, this detector itself, I've held one of these things because I built an instrument that used this Hawaii 2RG from Teledyne. And this costs more than the house that I live in right now. So it's very fun to hold these things. I'm sure you have many of them here at IAC. But the point is, when we have these sort of imaging detectors now that are sensitive to infrared light, we can do lots of it. We can start doing surveys of the sky. And these have been happening, of course, over the last 30 years, starting with IRAS, continuing on through Dennis. 2MASS was the survey that I used when I was doing my thesis. And then most recently, the WISE infrared survey, which went beyond the sort of near-infrared band, which is 1 to 2.5 microns, was able to detect even fainter objects out past 3, 5, 10, and 16 microns. So these surveys are really responsible now for the huge number of brown dwarfs that we have at our disposal and that we can study in detail. And, of course, one of the ways you would like to study these objects is to look at their spectra, because that's where all the information about their compositions and their kinematics are. So this is just a sort of summary slide of what the spectra of these different classes of brown dwarfs look like. At the top here is an M dwarf. The very youngest brown dwarfs can be hot enough to look like M dwarfs. In fact, many of the brown dwarfs we see in young star-forming clusters are late M dwarfs. They're just very, very young late M dwarfs. And then this is an L dwarf, a T dwarf, and this is actually not a brown dwarf. This is actually a spectrum of Jupiter. But the point of showing it here is that how similar these very cool brown dwarfs are starting to look like planetary atmospheres. And again, it's primarily because of the composition of the atmosphere themselves. These objects are cool enough to have gas molecules in their atmosphere, and so water is very common in M dwarfs, as is carbon monoxide. But in the T dwarfs, you start to get things like methane and ammonia and carbon dioxide in their atmospheres. All right, real planetary-like gases. So, and I should say that these spectra are very different. So they've given rise to 3 different new classes of objects. Victor mentioned a little bit earlier that I had done some work on L, T, and Y dwarfs. Here is just sort of a summary slide of what the properties are. The L dwarfs are just cooler than the M dwarfs, and they're unique because they get so cold that beyond molecular gases, you start to get condensate species in the atmospheres as well. All right, if you think about what is the hardest thing to melt here on Earth, those tend to be rocks and metals. That's why we build these big foundries to melt these things down. When you're going from very high temperatures down, those are also the first things to condense out. And so we see in the atmospheres of L dwarfs evidence of these sort of rock and metal clouds. Mark Marley likes to describe them as floating clouds of dirt. I like to think of molten iron rain raining on you, which does not make for a good picnic. But these are the kind of things that we're now seeing in these L dwarfs and have a very profound effect not only on the spectra, but also on their temporal brightness over time. I have a sweet spot for the T dwarfs because this is what I worked on in my thesis. But these are objects that are now cool enough to form methane. So the carbon monoxide converts over to methane, so methane becomes the main carbon-bearing species in these atmospheres. But you also get other gases like ammonia and CO2. And then most recently, just in the last few years, the next sort of spectral class has been uncovered, and many people were looking for these for several years, and it was really because of WISE that we're able to probe down to the very low temperatures below 500 Kelvin to see spectra that were fundamentally different from the T dwarfs. And in this case, we're starting to see evidence not just of these molecular gases like methane and ammonia, but also evidence of other types of condensed species, salt clouds and ice clouds. All right? So many, many species are happening in the atmospheres, which produces a very rich set of chemistry. Now, there's lots of exemplars that have emerged from the discoveries made over the last 20 years or so. Some of the most recent include some of our nearest neighbors to the sun. Many of you are very aware of this system, Lumen 16AB. This is the third closest system to the sun that has been found only in the last couple years. And it turns out it's a bonus because it's a two-star system. It's a double system. You can see its motion here it's so close that it actually shows up in some of the POS plates, but these later images are from 2MASS and WISE as it pops over there. Very high proper motion because it's so nearby, right? Only 2 parsecs away. And this system is so close that we can actually get very detailed observations of how its atmosphere changes as it rotates. And so there's this great study by Ian Crossfield just this year presenting a map of the surface of this brown dwarf based on monitoring the source with high-resolution spectroscopy. All right. So this is a pretty phenomenal thing that we can actually start to make a map measurement of a brown dwarf that's so nearby with the kind of observations we can do with near-infrared spectroscopy. Now, Kevin has been very famous for discovering nearby things. Here's the 4th closest system known. This is WISE 0855, and this object has an estimated temperature of about 250 Kelvin. So we've now broached the freezing mark. All right, we're now below 0 Celsius for the surfaces of stars. And you really start to question whether we can even call these stars at all. All right? This object has a much more planetary-like atmosphere and conditions than anything that we would look like in stars. And we're still trying to understand what its atmosphere looks like because it's so faint it's actually almost impossible to detect from the ground. My former student Jackie Fairty has just published a 2.5 sigma detection after 6 hours of time on Magellan, just photometry. So this is going to be a difficult one to study until we have things like JWST and the large telescopes. But the fact that they're there and they are so close really hints that there is quite a large population of very cool and evolved brown dwarfs. Now, we also know that brown dwarfs extend to very low masses. This is work done by Maria Rosa Zapatero Osorio back in 2000, but has continued on for the last 15 years, finding these very tiny, low-mass objects in young star-forming regions. Right? Again, these objects, when they start off very young, will tend to be hotter, but Maria Rosa and her collaborators are finding objects which are down in the L dwarf and the T dwarf regimes that are only a few million years old. And the only way you can have something that starts off that cold is it has to have an incredibly small mass. And so their estimated masses are somewhere around 5 Jupiter masses, and one starts to question whether, again, we can call these stars, or are these actually giant planets that perhaps have been ejected from their systems? Or perhaps this is how low-mass stars can form. This is an active area of argument among scientists in both the exoplanet and brown dwarf regimes. I don't know if there's a good way to solve this, but it is really starting to break down what we had long held as an easy concept of planet, because we're now finding this great diversity of these low-mass and cool objects. Those sort of former concepts have to be knocked away. All right. Now, all of this richness, all these very cool sources, all these very low temperature sources, are these things dark matter? Well, no, because you would have heard about that by now, right? Someone would have maybe Raphael would have got a Nobel Prize by now. It turns out, even though they don't add up enough to make up that dark mass, in fact, they're probably, as an aggregate, 10 or 20 times less massive than all the stars in the galaxy, so not even close. They still constitute a very large fraction of the objects that we see in the sky. Half of the current estimates, and this is within sort of a factor of 4 or more, that half of the objects in the galaxy are probably brown dwarfs. Now think about that for a second. That would be like every single one of you discovering that you have a child that you didn't know about. That would be news, wouldn't it? You'd be interested in that. Okay? So it's a vast population. So even if in terms of total mass it doesn't matter, it is something that we really have to sort of think about in terms of what is the actual composition of our galaxy. So this is a more updated mass function from Salpeter. Here's the Salpeter law. I'm now plotting low masses on the left, high masses on the right. So the Salpeter law is now increasing towards this direction. And, of course, we now know that this doesn't continue on all the way to the arbitrary low masses. It turns over somewhere around 1/10 of a solar mass. And how much it turns over, where it ends, if it continues to go down, or if there's a population of scattered low-mass planets that may be out there, is still a matter of a lot of debate. And you'll find answers in all sorts of directions. All sorts of wobbles off this end here can be justified with different studies. But we're still in that phase of trying to understand what is the extreme ends of star formation with these objects. So what are the big questions that we're now... So we've got thousands of brown dwarfs. We've got all these really cool discoveries. What are the big questions that still remain now that we've passed the discovery phase? Well, a big question remains is how do they form in the first place? But prior to 1994, you'd have no problem finding a theorist to tell you that brown dwarfs simply could not form. It may be because the ongoing accretion of material as these objects form in giant molecular clouds would simply continue until you achieved a sufficient mass to fuse hydrogen and blow out stellar winds. Right? That's a very favorite theory for why brown dwarfs didn't exist prior to 1994. Now, of course, we know they do exist, but the problem of how do you get a sufficiently dense clump in a giant molecular cloud, because you need very high densities to collapse something that's very low mass. Otherwise, thermal pressure keeps that from happening. How do you get very high density region, but then pull that object out before it has time to accrete more matter? That's one of the fundamental problems right now with understanding how brown dwarfs form, and there's no shortage of theories on how to solve it. So this is just sort of smattering of different ideas of how you might be able to make these dense clusters, but then keep them out from before they form, before they get more massive. You could start with massive clouds that just fragment and then dissipate. You could fragment the disks, so you're only worrying about radial direction, not the vertical directions in terms of mass. A very common theory, which is very popular right now, is that, in fact, these clouds that you sort of read about in your basic astronomy books are not these perfectly spherical cows. This is a joke for physics. Everything is a spherical cow. That they're, in fact, much more structured than that. And everyone who studies star formation regions knows this already, and it's just the theorists have to sort of get around to making sure that you incorporate these in as well. But when you have these very complicated structures, you have a lot more turbulence. You have 1D and 2D flows that are running into each other, and it may be at those intersections of flows that you're able to form dense regions, but then dissipate right away before you can accrete more material. You could also form these objects very early and then scatter them out. All right, the idea of clustering means that you have lots of different, or fragmentation means you have lots of different objects in the same region, and they're going to interact gravitationally. And so a very popular theory, again, is whether if you can eject out these proto-brown dwarfs before they have time to create material. And finally, there's an idea that perhaps in at least very massive star-forming regions, brown dwarfs may, the sort of cloud that's making a low-mass object may just be blown apart by the ram pressure and the photoions from very young stars. Now, we know that can't be the only reason because we also see brown dwarfs in low-mass star-forming regions, but that may be a possibility in high-mass star-forming regions. So the question is, do all of these processes take place? Do none of these processes take place? And is one dominant over the other? This remains an outstanding question, and one of the places where many groups are doing research, particularly in star-forming regions. Another big question is, do we really understand the theory behind these objects? When I say theory, I mean both the structural properties, the evolution, and also the atmospheres. And if we're talking about evolution and structure, one of the great resources for studying these objects are brown dwarf binaries, because, of course, in that case, you can make a dynamical mass measurement. And if you know anything about the atmosphere of the components, you can compare the prediction from the atmosphere to the prediction you get just from using Kepler's laws. And so there's been roughly a dozen of these tight brown dwarf binary systems have been followed up for the last year. This is just a most recent publication by Trent Dupuy and his collaborators showing the orbit of Gliese 417 BC. This is a binary companion to a young star where we know the properties of the young star very well. So we can borrow those properties to constrain what happens with this system. And what you get out in the end is that so this is the ratio of the measured mass to the mass predicted from the evolutionary models based on the luminosity of these objects. And you can see that there is a clear discrepancy for these two objects. So perhaps the models are not right. And we are just getting to the point where we can actually fundamentally test them and see what may be wrong. I'll also mention that there's only one eclipsing brown dwarf system that we know of in the sky. And unfortunately, it's an object in the Orion Nebular Cluster. And so one of the ways you also want to test structural theory is measuring radii. But we can't actually use the brown dwarfs we see in the field for doing that because this one eclipsing system is already a solar radius in size. It hasn't actually collapsed down to the point where we would actually be able to test theory. And this is a really interesting place to test the theory because when you look at predictions for the mass-radius relationship, the brown dwarf mass regime is right in a minimum of this relationship, balance between electron degeneracy over here and screening effects for electron screening effects in the core as you get to very low masses. And right now, the only real measurements we have for these are very massive transiting planets, such as these systems. But we don't yet have a brown dwarf in the field, an old brown dwarf in the field, that we can put on this chart as well. So that still remains something to be tested. The important point is that all of this depends on the equation of state of the interior physics, and this is well outside the laboratory regime. All right? We can't simply go in a laboratory and test what 10 to the 5 gigabars of hydrogen is going to look like at 1,000,000 degrees Kelvin. All right? That's not something that's going to happen anytime soon. So all of these are based on theoretical considerations of what the equation of state is, and the only way you can really test that is looking at the physical properties of these objects. Thank you. I've come back a couple times talking about the planetary atmosphere aspect of brown dwarfs. Of course, planetary atmospheres are becoming much more important because we actually have other planets to study, other planetary atmospheres to study outside of our solar system, transiting exosolar planets, and increasingly exosolar planets that we can directly detect with high contrast and high contrast imaging. Now, the atmospheres of brown dwarfs are at roughly the same temperatures. In some cases, if you have a young enough brown dwarf, it also has roughly the same mass and surface gravity. And the important thing is they are not near bright stars. And so you can study these objects to your whole content without having to worry about the block, sort of 10 million times light from the host star. And so we've been studying these objects in the perspective of planetary atmospheres, and we find lots of very interesting behavior that may be important and relevant for interpreting exoplanet climates. One of these is Victor mentioned I had done some work on the transition between the L dwarf and T dwarf classes. This is the absolute magnitudes at J band versus spectral type for something like 150 objects that have parallaxes. And you'll see a very unusual bump here. Normally, when you go to lower temperatures, things get fainter. That seems kind of obvious, right? But it seems that this region between the end of the L dwarf class and the beginning of the T dwarf class, there's a fundamental change in the atmosphere. For some reason, the condensates that are present in the L dwarfs very suddenly, and suddenly means, you know, 500 million years or something like that, disappear from the atmosphere. And as a result, all the light that was below that opaque cloud of dust is allowed to emerge, and it's much, much brighter at 1 micron than it is at other wavelengths. And so the fact that all of these brown dwarfs undergo the same transition questions whether this is a universal phase of condensate adjustment. Perhaps this is something that we should be seeing in all objects that cool from some point where they have condensates to some point where they have methane in their atmosphere. Right? This is something that still needs to be captured by the models. We're also, and I've shown this before, this great study by Crossfield, but plenty of studies now are looking at the temporal evolution of brown dwarfs, how they change with time. And we're seeing all sorts of remarkable phenomena that are, again, related to the cloud properties and the dynamics of the atmospheres. And so things like brightness variations have been observed, but also those brightness variations have amplitude modulation. Sometimes they vary, sometimes they go away, right? That would suggest some kind of evolution of the features on these brown dwarfs that happens over daily timescales, very short timescales. We also see the phase of those variations depends on the pressure of the atmosphere that we're looking at. Because these objects have very strong absorption features, when you look in and out of absorption features, you're actually looking at two different layers in the atmosphere. And when we do monitoring observations of those systems, we find that one part of the atmosphere is actually leading in the brightness phase as opposed to another part of the atmosphere. And that may be because the perturbations that are driving these variations are actually from internal physics, and so they're propagating outward, and we're seeing that propagation sphere. They may also indicate some vertical structure in the flows and dynamics of brown dwarf atmospheres. These are all observations that have been made just in the last few years, and so we are still trying to piece together what exactly we see, but there's a rich diversity in the meteorology of these objects, and that meteorology may also translate into some ideas on how to interpret exoplanet atmospheres. A really unexpected thing that emerged in following up brown dwarfs, and this was work by Ido Berger as part of his undergraduate thesis project. He got some time on the VLA and said, hey, I'm going to point the VLA at a couple of brown dwarfs and see what I see. And he saw what no one else would have expected, that these objects are radio sources. Now, they are cool, so you'd expect some amount of their thermal emission to be out in the radio, but of course that would be completely undetectable. All this radio emission is coming from magnetic activity. And the problem is when you look at the magnetic trends for late type M dwarfs and L dwarfs, H alpha and X-ray, which is sort of the traditional signatures for activity in these objects, completely disappear. Right? We see essentially no magnetic emission from objects right past the sort of ML transition. And yet we've been able to detect radio emission for objects way down to about 900 Kelvin. And importantly, this radio phenomena is not just, you know, we see some emission and we can go home and say we detected something. We see all sorts of different variations. We see quiescent emission. We see bursting flares. This is a great example of sort of pulsar-like behavior that we're seeing in some of these objects. You can also see it sort of emerge here in this radio image movie. What's driving this sort of pulsating behavior is still an open question. It may be that these objects are not do not have the sort of classic magnetospheres that we see in M dwarfs, where the emission is sort of distributed around the star, but it may be focused in very specific regions, perhaps auroral type emission like the kind we see with Jupiter and the interaction with the solar wind. Right? Then that would be modulated by the rotation of the object. That's one question. Right? Another question is, how do we actually generate these magnetic fields? These objects are fully convective, and so the traditional alpha-omega dynamo mechanism that powers the sun's magnetic field, very large-scale dipole magnetic field, is not going to be in operation in these objects. Now, a planetary science said, no problem. We know Jupiter has a strong magnetic field, so there should be magnetic fields around these objects. But these magnetic fields are thousands of Gauss. Right? Jupiter's magnetic field is maybe tens of hundreds of Gauss. So there's some additional driver for very strong magnetic fields in these objects that we still haven't identified. And finally, what is the source of all this plasma? If these objects are highly neutral in their photospheres, 900 Kelvin is very neutral photosphere, how does the plasma get up there in the first place? These are all questions that still have to be addressed. Last point I want to make is a big question, and keep in mind these are my personal big questions, so there may be other big questions out there. But now that we are in this phase where we're discovering many, many brown dwarfs, we know that they are abundant, we know that they are very long-lived, and we know that they change with time. It means that they potentially could be very important tracers of the galaxy at large, right? And so, and we know that they have existed through at least the bulk of the galaxy's age because we're starting to find brown dwarfs that for all purposes, appear to be halo objects, so must have formed very early on, or at least accreted into our galactic system from another place. So this is an example. So these are spectra of these objects. These are L subdwarfs, and this is actually the main project that I'm working on here with Nicholas and Jinghua, looking at these systems and trying to understand what their atmospheres are like, what they're made of, what their masses are, again, looking at the lithium test. And one of the interesting things, if you look at the kinematics of this source, so this source right here, 2MASS0616, was discovered by a colleague of mine, Mike Cushing. We measured its rate of velocity and its proper motion. We came up with a galactic orbit that looks something like this. Now, this may not be, very clear, so let me put it on a picture of the actual galaxy. All right, here's our sun. This is the calculated orbit for this object. Now, those of you who are very savvy in your galactic kinematics will realize this object is going backwards. All right, all the stars are going around the galaxy this way. This star is going in a completely opposite direction and very fast. So there's no way that this is an object that formed in the thin disk. This must be something that formed in the larger halo system very early on in the galaxy's history, or possibly has been accreted at some event in the past. But in any case, it really shows that these objects have been forming in our galaxy for, since its beginning. And that means they're still there, because they're not going to supernova, they're not going to evolve off, they're still going to be there. And they're going to retain an imprint of the chemical abundances of what they formed out of. And those chemical abundances are fully mixed in their atmospheres. And so these really are sort of chemical temporal tags that, if we can learn to disentangle those features in their spectra, can be very powerful in sort of mapping out the history of the galaxy, both in terms of star formation and chemical enrichment. Okay, so I'm going to switch gears now a little bit and talk a little bit about the project that I've been spending most of my time on, which is a spectral library from the SpeX Prism instrument. I'm going to go back to this picture of the spectra of these objects, just to remind you that there's a lot of information hidden in these things, not just the abundances that are present in the absorption features, but also the shapes of the spectra themselves are shaped by things like collision-induced H2 absorption, which is pressure-sensitive, and cloud opacity, which may be its own parameter in describing the atmospheres of these objects. And so because of the diversity that we've seen so far, about 6 years ago I started a project of essentially collecting, either observing or collecting from other observers, a large sample of spectra obtained with this instrument, which is the IRTF on Mauna Kea. This is the telescope. This is the instrument, which is SpeX. It's a sort of multi-faceted instrument, but the phase that I like and use the most is it has a low-resolution prism dispersed mode, which is very efficient and very sensitive. It's very much like the TNG instrument, which Michi's instrument. So, like I said, we've been collecting these data for many years, and so this is kind of a running movie of all of the spectra in order of spectral type, and only people who really love spectra will watch this and enjoy this. And over this time, we've now collected about 1,500 spectra of late M and L dwarfs, and we call this big data. Now, anytime I talk to about this in particle physics land, they laugh at me because 1,500 data points is, a microsecond of data. But given that we only know something like 1,000 or 1,500 brown dwarfs, this is actually a fairly large representation of the entire population, at least as we've discovered it so far. So why do we use this particular instrument? As I mentioned, this is a very efficient instrument, so it can get very high sensitivity for these cool objects. One of the issues with studying brown dwarfs is that you can't just point at one area of the sky with a multi-slit instrument and just get 1,000 spectra and move on like you do with galaxy clusters. Most of the time you're looking at these things individually across the sky. And so something that's efficient is very important for building a large sample. And it's also, even these are low resolution data, so we're not going to be doing kinematics with this work, and we're not going to be doing line profiles with this work, but many of the features that really describe the bulk physics, like the molecular features and the overall absorption from clouds and collision-induced H2, are broadband features. So we don't need high resolution to really study those properties. Now, it's also important in terms of exoplanet comparisons because the resolution of this particular instrument, Anamichi, is well matched to HST with C3, to GPI, which has just been commissioned on Gemini, to Sphere, which I forgot to put on there, and to Echo as it goes up as well. And so these will really be nice templates when we're starting to study the exoplanet atmospheres directly with these advanced instruments. So there's been a lot of science enabled, so I should say, this library is online. You can go and download as much of it as you want. It's been used in about 100 publications since it came out about in 2008, in all sorts of different science. So from source identification to classification, the classification scheme that Victor mentioned at the beginning for the T-Dwarfs was based in part on data that's in this library. Looking for rare objects, even the extragalactic folks have used this to sort out those pesky brown dwarfs that are getting in the way of their redshift 8 galaxies. That's fine. Okay. So I don't have enough time in this talk to go over all these different science cases, so I'm going to focus on just one in particular that we're spending a lot of time on right now, and that's looking at binaries that are identified from the spectra alone. So I want to take a step back and sort of summarize what we know about brown dwarf binaries in the first place. So my apologies that this is a little bit faint, but this is a compare plots from a review that I wrote back in 2007 on the properties of brown dwarf binaries. And the sort of three take-home points is as follows. First, we believe the binary fraction of brown dwarfs is pretty low, right? Somewhere between 15 and 25%, which is much lower than for M dwarfs, and is much, much lower than G dwarfs, and is much, much, much lower than, say, OBA stars, which are about 100%. And it turns out most brown dwarfs are also in very tight pairs. So this is a separation distribution. This is log of separation in astronomical units, and this is the distribution of the sources that were known at that time. The black histogram, by the way, are just young sources. It just distinguishes those separately. But you can see that's very strongly peaked somewhere around 1 to 10 AU. And in fact, something like 90% of the brown dwarf binaries that are known today, or very low mass binaries, are tighter than about 20 AU. We also see that they're mostly in very nearly equal mass systems. And again, this is very different from, say, G-star statistics, where you actually see more unequal mass systems. Here, most of the brown dwarf binaries have been found are very close to equal mass systems. So in fact, when we look at the trends as a function of mass for things like the binary fraction, the separation distribution, the mass ratio distribution, this seems consistent with sort of a mass-dependent trend from high mass stars to low mass stars. And if you compare this to models, they seem to agree quite well. So this is results from simulations by Matthew Bate, which was that movie I showed earlier, showing the multiplicity fraction as a function of primary mass. All the blue bins here are the observations, the measurements of the binary fraction. The black line here is predicted from model, and it agrees great. So everyone should be happy. There's no problems, right? So one thing I want to make sure to emphasize, particularly for the students in the room, is that just because two things agree doesn't mean that they're both right. Right? They may be both wrong in exactly the same way. And the evidence that this may actually be a spurious result, if we look back at the separation distribution, so here's that same separation distribution, log separation versus number, you see this nice Gaussian peak, all right? Something like over 90% have separations that are greater than 1 AU in this distribution. Now, if I show the same plot not as the projected separation, the physical separation of the binary, but as the apparent separation on the sky, we see an even sharper peak that ends very abruptly at about 0.1 arcseconds. And for those of you who are familiar with high-resolution imaging, know that 0.1 arcseconds is about as tight as a system that you can resolve with adaptive optics or with HST or whatnot. So something like 90% of the known binary systems have been resolved with these instruments. And so it's no surprise that there are very few tight binaries over here observed. The question is, are there many tight binaries that actually exist? Going back to that plot that showed the agreement between models and separation, it turns out the models themselves are also not looking at tight separation binaries simply because the computational load to go from a 1 parsec molecular cloud to a 1 AU binary is very prohibitive. And so they stopped resolving these systems at something like 5 AU, which turns out to be about the peak of our binary distribution observed. So two rights don't make a right. Sometimes two rights make a wrong. And so we've been interested in trying to probe closer separations in here, and so have other groups using various techniques, radial velocity variability, microlensing, astrometric variability, And the numbers are all over the map, right? If you look at just this sample, it's less than 1%. Some results go from 1% to 12%, all the way up to 32%. More than half of the spectral binaries could be closer than 2.6 AU. That's a big uncertainty. So how do we probe this efficiently? Well, in the last couple of years, we've been developing this technique to use that library of spectra that I mentioned to find binaries, not by resolving them, but by looking for blends. We're looking for spectra that are actually blends of multiple components. Now, this is a very common technique in the white dwarf, M dwarf world. It's very easy to find these blends because when you look at the red end of the spectrum, you get something that looks like an M dwarf. When you look at the blue end of the spectrum, you get something that looks like a white dwarf. And you can decompose that spectrum and actually measure the properties of these two sources without resolving them. So you're identifying binaries and characterizing their atmospheres without actually resolving them in the first place. It turns out we can play the same game with the brown dwarfs across the LT transition. So here's just one of those many spectra in our library. For most of you, this is going to look as sort of squiggly line as everything else. And those that stare at these spectra over and over again, it looks a little odd. To show why that's the case, if I just look at, say, the left-hand side of the spectrum, which is maybe shortward of 1.4 microns, I can easily find another spectrum in my library that looks just like it, something like a early T-dwarf. If I look at the right end of the spectrum, again, I can easily find something that looks just like it, in this case, something like a late L-dwarf. If I try to use those same templates to match the whole spectrum, neither of them work. In fact, you try to do this with our entire library of 1,000 spectra, 1,500 spectra, you can't find a single object that looks like this one. It's unique. It's different. If, on the other hand, I take 2 of the spectra in our library and I make a binary template, you can get an almost perfect match. So this is an illustration of how this technique works. We literally make hundreds of thousands of binary templates from our library, and then we see if that is a better match, the spectrum we observed, to just one of the single templates in our library. And in this way, we've actually found many dozens of these systems that look like they're binaries but are not resolved. They're spectral blends. And fortunately, some of them are resolved after the fact. So this is an HST image of this source. And while you might have a hard time convincing yourself that we actually resolved the system, it turns out through modeling that this is, in fact, the right separation and the right relative magnitudes to match the spectral modeling that we've done here. So several of these objects have been resolved in this way, so that's this example right here. We've also started to find that these objects, that these spectral binaries that we find are also astrometric variables. That's the case for SCS J0805. We identified in 2007, and then it's been identified as an astrometric variable. In that case, something like a 0.9 to 2.3 AU separation binary. Here's another system which is a lot more difficult to pull out as a spectral binary, but when we monitor it with radial velocities after the fact, or I should actually be clear, when another colleague of ours used KeckNurSpec for 3 years to study this object, they also determined that it was a radial velocity variable. So this, by the way, took 3 years. This took about 20 minutes. So it's a little more efficient this way, right? Now, it turns out when you have some knowledge of the atmosphere and some knowledge of the masses, either from an orbit or radial velocity variability or something like that, you can actually start to make some really stringent constraints on the properties of these systems. And so this is my collaborator, Kellen Blake, and together we've been doing some modeling where we can actually take the properties that we get from the spectral binaries, the luminosities of the 2 components, and the properties we get from the orbits, and make both mass and age constraints on these systems. Remember, brown dwarfs change with time. And so if you just see an L dwarf, you don't know if it's a brown dwarf or a star. You don't know if it's a young or an old object. But if you can have another piece of information, like having the mass constrained, you can actually break that degeneracy, and we can now use these as benchmark tests for evolutionary models. Here's another example. This is a binary, which is this system right here, which turned out to be a common proper motion companion to a nearby M dwarf. Again, we identified this as a spectral blend, but then we got the radial velocity measurements that showed that there was this clear signature of variation. And because this object, which is an M7 dwarf, is inactive, almost all M7 dwarfs are active, so if you see an inactive one, it means it's pretty old. We can combine the information from this and the age information we get from this spectral binary and compare them and see if they match up with the models, and indeed they do. So in this case, we actually find agreement between the evolutionary models and what we get from these systems. Some of these systems are really quite exotic. I mentioned earlier that there's almost no H-alpha or X-ray emission when you get past the ML transition. In fact, there are a few unusually active, we like to call them hyperactive, they're like little children running around screaming and yelling, that have very strong emission. And they've been a mystery for about a decade. We don't know how they can power so much emission when everything else is completely quiet. Well, it turns out that this particular system, which has been active over a decade, you can see the very strong H-alpha line that's present in this absorption, also has a companion, which we identified as a spectral binary. Now, that companion in itself is probably too far to be inducing any kind of magnetic interaction. But because it's there, we can actually figure out roughly what the age of the system is. And it turns out that this is a pretty old system as well. So this adds another piece to the puzzle. We have a very low temperature object, which is very old, and yet incredibly active. And it may be that it turns out that when we think about activity among stars, it's usually the older stars that are less active. It may be that the older objects among brown dwarfs are more active because they're more massive. And so there's an idea now that was proposed by Christensen et al. That suggested that the magnetic activity of brown dwarfs may be scaling with mass more than it does with age. And this is a piece of evidence that may actually be true. Let's get that guy. Just recently, we have identified one of the nearest spectral binary systems. This is an object that was just reported by Schultz et al. This year. Again, we took about a 10-minute spectrum of it and realized right away that this was, in fact, a binary system with an M dwarf and a T dwarf. And we were able to just barely resolve it. This is about 0.14 arc seconds in separation, but 4 magnitudes different in brightness. So this is a pretty challenging observation even with Keck. But the fact that it's that close and we can resolve it means the separation is about 1 AU, which means the orbit is something like 3 years. And so we are now following this up with rate of velocity variations and imaging so that we can get a 3D orbit for the system and actually get very precise masses out of this very nearby system. One little piece of trivia, by the way, there's about 13 late M dwarfs within 10 parsecs. 2 of them are binaries, and both of them have brown dwarf companions. Both of those are brown dwarf companions. So there may be lots more brown dwarf companions out there that we're not seeing, but we can see with this method. So what's the bottom line of this work? Well, this is the thesis project of my student Daniela Barales-Cagliuffi, who, by the way, was here, I think, maybe 3 or 4 years ago, 5 years ago, as a student, a summer student doing research. And she's looking at the separation distribution of the systems that we're able to resolve or at least follow up with radial velocity or astrometric variability. And what she finds is that the spectral binaries we're finding, which are, so this is now all the known systems as a function of period and the number. These are all the known systems. The blue ones are all direct imaging, so you can see the sort of bias toward direct imaging. And all the purple ones are spectral binaries. And, of course, what we're finding is most of those are at much closer separations than the imaging. Right? So something like half, the average separation is like half that of the entire distribution. So we think we're seeing some pretty clear evidence that, in fact, there's a large population of very close binaries that are out there that are simply being missed because they're too tight to be resolved. And then this is some support with models. There's a recent paper by Jumper and Fisher where they looked at turbulent fragmentation theories and were able to show that the distribution of expected brown dwarf binaries was something like 1.6 AU or 6 years. Right? 6 years is about here. That's the median from their simulations. If that's the case, reflect this over to the other side. We've got lots of binaries that may be out there. So that binary fraction may just be a lower limit. There may be a lot more systems out there that remain to be found, and this is one of the ways that we can find them. Okay, so just some closing thoughts, since I'm already at an hour. We're kind of past this age of discovery. So when I was a graduate student, we were in the sort of age of discovery, right? It's Columbus going off across the ocean, finding new lands, putting their flags on them, okay? We're well past that age because now we have thousands of these objects. But that's actually a more interesting age, right? Because there's so many objects out there. There's so much diversity in their properties that we're really able to now really probe the physics of these objects. And I like to come back to, what are the fundamental physics of what's going on in their atmospheres, in their interiors, and even in their environments. So things like the equation of state of the interiors of brown dwarfs and the generation of magnetic fields, and even just the basic chemistry of their atmospheres are all questions that we can now statistically answer because we have such a large sample. So I think this is going to be it's sort of less exciting time because you don't get to be on the cover of Nature every time you find a brown dwarf, but it's a more interesting time because there's a lot more questions that can be resolved. And so I think, as we start to push down to lower temperatures, this diversity is going to get even wider. And as we start to have observations with exoplanets, where we actually have spectra of exoplanets that we can compare to these brown dwarfs, I think we're going to find a lot of surprises and a lot of similarities between these two different types of objects. And of course, as I mentioned earlier in the talk, we're in this phase where we have to start challenging the assumptions that we had made before we had found this whole class of objects. And the biggest one, of course, is what is a planet? What is the definition of the word planet? Right? It may not be just as simple, we can cut a mass off at, say, 13 Jupiter masses, and we'll call everything on one side a planet, one thing a brown dwarf. Because that's not necessarily related to how they form in the first place. And so I think it's very exciting that we're starting to find these very low-mass objects, not just in star-forming regions, but also out in the field, and we can see how they evolve over time. And if it turns out that we have lots and lots of these objects, that's really going to say that maybe we need to get, so this is going to be a bold suggestion, but maybe we need to get rid of this word planet entirely and think of another way of classifying objects that are, like planets, almost like planets, free-floating planets. There's a lot of these sort of phrases that are very inexact, and I think we're going to have to start thinking a little bit more about the broadness of this term than we do currently. And I will stop there. Thank you very much.
Okay, thank you very much, Adam, for this very interesting talk. So now it's time for questions.
Yeah, I have some physics questions.
Sure.
The cosmology pie chart that we started with.
Yeah. You want me to go back to it?
Not really. I think we know what it's like.
All right.
That entire pie chart can come just from a CMB observation.
Right.
Could you just recap what your goal was with the dark matter bit of the pie chart? Do you really want to fill that up with brown dwarfs? Because if you do, then you disagree with the CMB.
Well,
go on.
So we know brown dwarfs are nowhere near enough common enough to make dark matter.
So could you give us another version of that slide?
Another version of that slide.
Just tell us again what you meant by putting that up in.
Well, historically that was a motivation for finding brown dwarfs.
Historically, fine. I think that answers that question then. Okay. Next question. Is could you go back to the slide on the mass function of stars, basically the latter of the two?
The cartoony one?
No, not the cartoony one. The most updated one that you showed with the turnover.
Okay. That one, yeah? No?
Yeah. Okay.
Yeah. Okay.
What happens if you put planets on there?
If we put planets on there.
I realize we can't see any at the moment, but if we extrapolate.
So if you assume that, current estimates are there's something like half or one planet per star in the universe. All right.
Okay.
So you could take the.
Let's call it one.
Okay, let's call it one. So you could take the left side of this plot and mirror image it over to the right side of the plot.
Okay. Connected, which brings me to the next question, I think, which is what's the physical origin of the peak in fundamental physics origin?
So that's a good question, and there's a lot of people thinking about that. It may be that that peak has more to do with the physical properties of the gas in which these stars form out of, so things like the mean molecular weight of a molecular cloud or the sort of average temperature of molecular clouds. There's been some work looking at if you have a molecular cloud that starts at, say, 100 Kelvin as opposed to 10 Kelvin, that will shift that peak over, in that case, to higher masses because you have a higher temperature, so you need higher masses to actually initiate collapse. So if it turns out that the average clouds are much hotter, and which would be the case, for example, in a metal poor cloud where you don't have the metal lines to cool off in terms of radiation, then you may end up pushing these stars to higher masses and pushing that peak over to higher masses because of that. Now, that's been one of the main arguments for why we think population 3 stars, for example, are going to be very massive stars. But I think that's the jury is still out whether that's a big enough shift, if that's a big enough factor in shifting the masses over. So in terms of theory, it maybe has to do with these fundamental properties of the cloud itself. In terms of observations, we don't really even have a good enough measure of what happens on the other side of the peak. So I think until we actually have and I should say for the field. So young clusters, we actually have very good measurements around that peak. But in the field, we don't. And we certainly don't have for metal poor environments, other galaxies, those measurements stop way out in the sort of F and G star range. So until we have those measurements, we can argue about what drives the peak, but we don't actually know if that peak varies in reality. Does that answer your question?
Yeah, I think so.
Yeah, okay.
Why does it have to be a mirror image? Try the previous one. And then I'm gonna
that was just a guess, right? So, so if there's very few O stars, you can put whatever you like, and you can put it in any shape you like. Okay.
So, what are the perspectives of using CanaryCam for, pushing the knowledge in this field?
For CanaryCam?
Yes.
Will you give me some parameters for CanaryCam?
Well, maybe
I'm not as familiar with the instrument, so.
Yeah, well, maybe I can tell something. So I think the advantage of CanaryCam is an instrument in the mid-infrared, and going to the mid-infrared is where some of the coolest objects emit most of their light. So this is, I think, that in particular CanaryCam is a very good instrument to try to map all the solar vicinity, in particular to search for components around the nearby stars, because as Adam Burgasser has shown, we are identifying very close brown dwarfs in isolation with very cool temperatures, and these objects are very difficult to identify in the near infrared and in the optical. So we had to move to the mid-infrared. So in that sense, I think the CanaryCam offers a unique opportunity to detect this kind of objects.
Are you planning something like a survey with CanaryCam?
In fact, we are doing.
Thanks, Victor.
Okay, so some more questions? So if there are no more questions, so let's thank Adam Burgasser again. Okay, and just remember that now we have the scientific coffee in the library.